only the second time I've seen Tom talk. If you first you know I work at Intel, and I have an interest in describing hardware in functional languages. A few years ago, we ran a little invitation-only workshop where we sort of found people who looked like they were doing interesting stuff to describe hardware with functional languages, and we invited them to come. And Tom was one of the guys we invited, and the talk was fantastic. So I don't mean to build up something.
Yeah, this is not going to be that great, so.
I've been really looking forward to seeing him talk again. So then you tell us about now controlling hybrid vehicles with Haskell.
Okay. Well, good morning, everybody. My name is Tom Hawkins. I am from Eaton. I just want to thank Jim and Simon for inviting me here today. Today I'm going to be talking about how we use Haskell to design hydraulic hybrid vehicles. Hydraulic hybrids are pretty much the same. They work pretty much the same way as electric hybrids, but instead of using batteries and electric motors, we use hydraulic motors and hydraulic batteries. The real benefit with hydraulic hybrids is they have greater power density than electrics. So with that said, they're going to be targeted for heavy-duty trucks as opposed to passenger vehicles. Today, I'll just give a little overview of the company Eaton. We'll talk about the basic components that go into a hybrid vehicle, a hydraulic hybrid vehicle. And then we can look at a little bit of how we use Haskell just kind of on our day-to-day activities. And then we'll take a closer look at an experimental DSL that we're developing called Atom, which allows us to design embedded control software to control these type of systems. And then we'll wrap up with some of the challenges that we've had to overcome. So Eaton's a big company, about 80,000 employees worldwide. We did about $13 billion in sales last year. The company itself is in diversified power management. So that basically means all the products we make and sell have something to do with managing power, whether it's electrical power, mechanical power, or fluid power. There's five primary groups. There is the electrical group, the aerospace, truck, automotive, and then the group that I belong to, hydraulics. Within hydraulics, we make essentially everything related to hydraulics. Valves, pumps, motors, cylinders, actuators, fluid conveyance, fluid filtration, and Gulf grips. I have no idea how this fits in our portfolio, but it's actually really profitable for us. We own 80% of the market share in Gulf grips. I don't know if there's any avid golfers out there, but the brand is Gulf Pride. Who knows? So a little bit about hydraulics. The basic component in a hydraulic system, the key component is the valve. It's important because it provides a control import, a way to control these systems. A valve, you could have a manual lever that opens and closes a valve. Or in software, we could set a bit in software, and that bit's going to energize a solenoid, which will open or close a valve. There's all sorts of different types of families of valves. The valve here is very common. This is known as a proportional directional control valve. Now, if we're talking about hybrid vehicles, we need a way to store energy. And the way we do that in hydraulics are with these things called accumulators. Now, the concept is very simple. Essentially, what you have is a steel tank that you fill with typically nitrogen gas. And then to store energy, you simply pump fluid into that tank, compressing that gas. So that gas is just essentially acting like a big spring. There's two types of accumulators. There's the bladder type, which you see on the top here. And then there is the piston type of accumulator. The bladder type is essentially there's a little balloon inside the accumulator, and that balloon gets compressed. With the piston basically moves up and down inside that accumulator, and the piston separates the air from the oil. But the real cool component in these systems are the pumps and the motors. I'm not a mechanical engineer, but when I joined Eaton last year, I was pretty amazed when I first saw how these things work. The pump that we use on the system that I'm currently working on is known as an axial piston swash plate pump. And I actually brought in part of the pump today. This is the rotating group of the pump. And the way it works, it's pretty interesting. The rotating group itself is basically a group of pistons. There are 9 pistons in here. I'll pull one of them out so you can see it. And on the other side of the rotating group, there's porting that accesses all those barrels inside this housing. Now, there's a metal plate that goes over the top of this. I didn't bring it in, but it's called a valve plate. And essentially in the valve plate, there's 2 holes cut into it in the shape of kidneys. And what the valve plate essentially does is it divides the pistons into two groups, the pistons that are sucking oil into this thing, and then the pistons that are pushing oil out. On the other side of the pistons, I'll pull one of these guys out, is a ball joint. And attached to the ball joint is this thing here called a shoe or a slipper. And it's kind of tough to see, but there's a hydrodynamic bearing on this side of the shoe. What this shoe does is it rides on a flat plate of metal called a swash plate. And that swash plate, these pumps are very interesting. They have this nice property that you can control the displacement of the pump per revolution. And you do that by varying the angle of the swash plate. So I don't know if everybody can see this, but let's say my hand is a swash plate and all of these shoes are riding on the swash plate. If the swash plate is perfectly neutral, as this rotating group spins, the pistons don't do anything. They just stay where they are. However, if you were to put a displacement on the swash plate like this, as the group rotates around, the pistons stroke back and forth. It's kind of easier to see with that picture there. Actually, I've got a video. Here's a CAD model of one of our pumps. This is the rotating group right here. These are the shoes, and it's kind of tough to see, but here is the swash plate. So in this video, you'll see the swash start to move, and what happens is on this side of the pump, the pistons are riding down that swash plate. On the other side, so this side would be pulling the oil into the chamber, and on the other side it would be pushing the oil out. Now the real cool thing about hydraulics is the power density. This thing is not very heavy. It's about 30, 40 pounds, and it's not all that big. I mean, it's about the size of a milk jug. This little motor here can accelerate a 70,000-pound truck faster than a 400 horsepower diesel engine. So if you think about a diesel engine about that big, it would be approximately maybe this long, about that wide, and easily this tall. So it's a pretty amazing piece of machinery. Now, if you think these are cool, there's another category of pumps called bent axis pumps. These are also piston pumps. These pumps have a little bit more mechanical complexity, but they are much more efficient than these pumps. These pumps get about high 80s, best case. Piston pumps, these bent axis pumps can get up to about 92 to 95% efficiency. And the way these vary their displacement is by moving the entire rotating group. So instead of just moving a swash plate, this whole rotating group rotates and bends that axle there. And then here's a video that shows how these pistons stroke back and forth as the pump rotates. Now, how do we take these components and build a hybrid vehicle? Well, it's actually pretty easy. So let's take a conventional truck chassis. It's got an engine, transmission, drive shaft, and rear diff. And then what we'll do is to the drive shaft, we're going to mount one of these axial piston pumps. And on one side of the pump, we're going to connect a reservoir full of hydraulic fluid, oil. And on the other side of the pump, we're going to connect a high-pressure accumulator. Now, when the driver takes his foot off the gas and steps on the brakes, instead of using the brakes to slow the truck down, which would essentially burn off all that kinetic energy to heat, what we're going to do instead is we're going to put our pump into stroke. And the way we do that is by putting a displacement on the swash plate. Now, this is going to start pumping oil from the reservoir through the pump into the accumulator. And this is going to slow the vehicle down and bring it to a stop. Now, when the driver takes his foot off the brake and steps on the gas, instead of using the gas to launch the vehicle forward in the engine, what we're going to do is we're going to put our pump into the opposite stroke. So move the swash plate to the other side. And essentially what we've done is we've converted this pump into a motor. So now all that high-pressure fluid that we've stored in the accumulator will motor out through this rotating kit back to the reservoir, and this is going to launch the vehicle forward. Now this is pretty cool. This is called a parallel system, meaning the hybrid components are parallel to the conventional drivetrain of the truck. Eaton has branded this hydraulic launch assist. This is our first venture into hydraulic hybrids. But we can do actually much better than this. So now what we're going to do is we're going to get rid of the transmission and the drive shaft and the rear diff. In its place, we'll put a pump, we'll put a couple of motors on the rear wheels, we'll add a high pressure and a low pressure accumulator, and then we'll lay down some plumbing. So there's some high pressure lines, and here's some low pressure lines. Now the engine is basically just charging up the accumulator, and the motors are using that charge. So this is known as a series configuration, and this is nice because we've completely decoupled the engine from the wheels of the truck. It allows us to run the engine at its optimal RPM. Here's just a CAD model of the system. We've got the reservoir over here. This is that long tube. This is the high pressure accumulator, and this is the pump unit. And then this is a transfer case that connects the pump to the drive shaft of the vehicle. The most important part, though, obviously, is the electronics and the software, and that's in this little box right here. The mechanical engineering is kind of interesting, but it's, it's just metal and oil. Okay, so these trucks are good for, the system is good for heavy-duty trucks. And because it's a hybrid, it's going to get its most economy or fuel-efficient economy from trucks that do a lot of stop and go. So what trucks are really, really heavy and stop and go all day long? Buses? Well, that's our second program, but I heard it over here. Garbage trucks. Yay, it's been a lifelong dream of mine to work on garbage trucks. Actually, I didn't know it at the time, but I've got the dream job of 5-year-old boys everywhere. We went to San Diego to visit some friends, and they had a couple of kids, and they asked me what I do for a living, and I told them, well, I design and test drive garbage trucks, and their eyes get really big. You tell this to an adult, and they say, oh, don't take it too hard. The economy is really bad right now. You'll find something else. Okay, so we use Haskell for all sorts of cool stuff in the office. Unfortunately, I don't have time to talk about it. So if you see anything up here that catches your eye, come up afterward, and I can fill you in. Well, let's quickly talk about Atom. So Atom is a DSL that we're working on, and it's heavily inspired by BlueSpec and to some extent STM. Like both of these systems, BlueSpec, most of you are probably aware, is a high-level hardware description language, and STM, a relatively new model for concurrent computation. Like both of these systems, Atom is based on this notion of atomic state transitions, or more specifically, atomic state transition rules. But what we're doing is we're using this to actually build embedded software that we can drive and control these vehicles. The idea of taking all the good stuff of Haskell, adding these rules, and potentially allow us to create safer software. So it allows us to concisely express safety-related behavior in our system. Why do we care about safety? Well, we're dealing with very high pressures. These accumulators can exceed 5,000 psi. So if you open a valve at the wrong time or you pull a clutch when you're not supposed to, metal parts can go flying off in all sorts of fun directions. The other reason safety is important is these vehicles are riding on the road with you and me, so we have to look out for the safety of the driver and the safety of everybody around the driver. But the most important reason is we're dealing with garbage trucks here, so we don't want to accidentally launch a fully loaded garbage truck into somebody's living room, and that would be a disaster. I mean, you could see the headlines, hybrid garbage truck crashes family reunion. Al Gore to blame. But aside from all this nice, high-level, concise code, Atom actually does some stuff for us automatically. It allows us to do thread scheduling, multi-threaded, multi-rate programs, but do the scheduling at compile time as opposed to runtime. So we don't need an RTOS to do the task scheduling for us. But more importantly, it handles the thread synchronization. So we don't have to mess with locks and semaphores. And then one other thing we're looking at is possibly using this to automatically partition a design across multiple vehicle ECUs. So here's a simple Atom program, a checking account essentially. We've got a balance and 2 rules that handle deposits and withdrawals. Each rule has two things. They have enabling conditions and actions. The enabling conditions are the things that need to be true before the rule is allowed to execute. The actions are what is taking place, what variables are being updated. The important concept here is each of these rules executes atomically. If a rule is selected to execute and its precondition is true, all the actions are going to take place or none at all. Just a few things from the Atom API. Atom has 3 fundamental types: system, var, and term. System is essentially a monad that collects all the design descriptions, so all the variables and all the rule declarations. Vars are immutable variables. Terms are nothing more than combinational expressions of those variables. And system, it's probably a bad word to use, but system is what we use to actually design a rule or define a new rule. When allows us to add an enabling condition, and then we have an assignment operator as well. Here's a simple example. So HLA's got this clutch that connects to the drive shaft of the vehicle, and we like to disengage that clutch under certain circumstances. For instance, if the ABS comes on, we want to get out of the way. And this is some chunk of code that allows us, well, the problem is if we command a disengagement, but the clutch doesn't disengage. So this is a safety monitor to check for that condition. I think I'm going to go on because I don't have much time here. So let's talk about scheduling. So as I mentioned earlier, Atom can schedule threads at compile time as opposed to runtime. So a thread essentially in this environment is nothing more than just a set of rules with the same execution period or execution time. What the compiler is going to do is it's going to return a single C function for us that we need to call at the base rate of the system. So what the compiler attempts to do is it attempts to balance these rules. It attempts to schedule these rules such that the execution time of that function is minimal. So here's an example. We've got 4 rules in our system, A, B, and C. And rule A needs to execute every 1 millisecond, and B, C, and D need to execute every 2 milliseconds. Now, a naive implementation would be to simply execute all the rules on one sample, and then on the other sample, just execute rule A, and then toggle back and forth between those two. The problem is it's not very balanced. You've got your worst case of 30 execution units, whatever that means. What the compiler can do is it can move these rules around such as to balance or at least lower the worst case execution time. Now, we're talking about hard real-time software here. This is stuff that needs to execute on a deadline, otherwise parts go flying off. And so what we want to do is we want to minimize that time. There's all sorts of advanced ways we can compile these systems, but I don't have time to get into it right now. So really the point here is we can do scheduling at compile time as opposed to runtime. This allows us to at least semi-verify the timing of our program at compile time as opposed to having to get out on the bench and verify timing. But the real key here is thread synchronization is handled for us. We don't have to mess with locks and semaphores. And the way the compiler does this is it just merely needs to adhere to rule atomicity. Then the other thing we're looking at, and we just started this, is multi-ECU partitioning. So with our current HLA system, we only have a single ECU. ECU is essentially a vehicle computer. But our series program has multiple. I think we've got 5 or 6 in the series so far, and they're connected via some network topology. Well, instead of programming each one of these ECUs independently, it would be very nice if we could just program the system as a whole and then let the compiler allocate that. So again, program the system as a whole, let the compiler handle how software is allocated to each vehicle computer, and then also handle all the communication and synchronization between the vehicle computers on board the vehicle. The catch here, though, is safety. The primary reason to go to a multiple ECU architecture is for safety, is for redundancy. So what the compiler needs more information. The compiler needs essentially availability and integrity constraints on the individual components in the system. And then also the designer may need to specify which rules are the really, really important rules that need to be executed versus which rules are well, it'd be nice to have, but they're not necessary to keep the truck running. We've had a lot of technical challenges, but the biggest challenge is just getting functional programming in the door in the company. I've been with 2 former employers where I attempted to get FP in widespread use, and I didn't get anywhere. So what did I do? I found another job. But Eaton is different. Eaton is very open-minded. It's a very interesting company to work with, and they're so far we're having luck getting functional programming in the door. Really, my only words of advice is this. So functional programs, they have this expression. With functional programming, you declare what to compute, not how to compute it. Now, I've always struggled with this, but I finally realized what this expression means. What this means is when your boss comes to you with an assignment, you need to declare what you're going to compute, just not how you're going to do it. Or in other words, the old mantra. Thanks a lot, guys. I really appreciate the opportunity to come with you and talk today. This is one of our fleet trucks that's currently picking up trash in Denver right now. Questions? Yep.
Is it just you working on this, or do you have other people programming Haskell as a company?
We've got 3.
And how has that process gone in terms of bringing people in?
Good. I mean, we actually hired two new engineers, relatively new. And they hadn't had functional programming experience before, so it's been a learning process over the last couple of months, but once they see this, they're very excited about it. Out of Eaton, out of 81,000 people? Eaton is unique in that they're kind of an old school company, a hydraulics, metal, oil company. They're not very into software, but they're going through this transition right now. So in the company, at least in hydraulics, there's probably less than 30. So it's a good environment to get this in. Anything else?
If I'm not lucky enough to work with garbage trucks, will I ever get to programming in Atom?
Sure. I mean, I have been pushing it out. Just I've been so busy lately. I haven't made a release lately. But up until a few months ago, it has been open source, so it is available. Yes and no. The fault monitor that I showed up there is actually implemented, but it was hand compiled as opposed to automatically compiled. We may get it into our first application is refuse, so we may get it into refuse, depending on how the schedule goes. But our plan is to get it in the follow-on program, which is shuttle buses and city buses. All right, thanks.